Multi-head self-attention for natural language processing time series data. Attention allows a neural network to focus on specific, relevant parts of its input or previous output sequence when making a prediction or generating new content. Self-attention means that this focusing happens within the same sequence. For example, when processing a particular time series patch, the model considers how relevant all other patches in the input history are to understand the current patch. For example, if we are working with a time series, our model considers how relevant all parts of the input data are to understanding the current patch. How it would work for a single attention would be, for the data in the input sequence, we generate three things: query, key, and value. Query represents what the input data is looking for, similar to asking a question about the current input. Key is a summary of what each piece of data in the sequence contains. Think a label. And the value is the actual information. We get these by taking the vector representation for each input element and multiplying it by 3 learned weight matrices. For each query vector, its similarity is calculated with all other key vectors in the sequence. This is usually done with the dot product. A higher dot product means higher similarity or relevance. We then divide by the square root of the dimension of the key vector. This stops dot products from becoming too large, which can lead to small gradients during training, also called the vanishing gradient problem. Then we softmax the scaled similarity scores. This normalizes them into a probability distribution. These normalized scores are the attention weights. This tells us how much attention the current element should pay to every other element in the sequence. Finally, these attention weights are multiplied by the value vectors. This creates a weighted sum of the value vectors. Elements with higher attention weights, which means higher relevance, contribute more to the final output representation of the current element. For multi-head, we project the initial input into multiple different subspaces using H, different sets of learned weight matrices for query, key, and value. For each of these H sets, we then perform the scaled dot product attention calculation independently and in parallel. This uses a GPU for parallel computing. This allows each head to learn different types of relationships for different aspects of the input. For example, in time series, different heads might capture short versus long-term patterns or trends. We then concatenate the outputs from all H individual attention heads. Then we pass the concatenated output through a linear layer with a learned weight matrix to project it into the desired output dimension. This is truly groundbreaking work because it allows the model to weigh the importance of different parts of a sequence to each other from multiple perspectives simultaneously. This means the data is extremely contextual and can handle a wide variety of sequential data.